Now, in this lecture, we will see element stiffness matrix for 1D bar element. We will derive using generic form of K. Okay. So, in last lecture, we have seen this is the generic form, where B is a strain displacement relationship matrix and D is stress strain relationship matrix. Okay, let's write this for 1D bar element in 1D space, as we always take the simplest case, x equal to 0 and x equal to L. This is our 1D bar element, and other two dimensions are given as A, okay, cross section area, uh, which is given as the element section property. So we can say dV is A into dx, area into length. Okay, and the integration over volume of element will become integration over length of element, because this is 1D element and we have only length as a physical dimension. So this is the element stiffness matrix. Okay, but still we need to find B and D. So let's see. Let's focus on B, strain displacement relationship matrix. So for 1D case, we know the strain displacement relation is epsilon x is equal to dou u by dou x from our continuum mechanics lecture. So since this is a 1D space, we will have only sigma x and epsilon x. So only one stress and strain component. So here we will write it as a strain vector. Remember that stress and strains are tensors, but in FEA we represent them as a vector for computational convenience. Okay. So strain vector is a dou u by dou x, okay, which is 1 by 1, okay, because we have only one stress and strain component. Now we need to give this u as we know is a solution function. So in FEA the fundamental concept is that we assume the trial function, okay, and we represent it as a discrete function. That means we represent displacement as a displacement, I mean we represent displacement in form of displacement at node 1 and displacement at node 2, okay. And elsewhere we just interpolate the solution using shape functions 1 minus x by L and x by L. So this is n1 and this is n2. So n1 u1 plus n2 u2. In a matrix form, we can write it as a n transpose and u e. Okay, so displacement vector for element. Now let's substitute this u in our strain function here. So epsilon e is equal to dou by dou x, okay, n transpose u e. So we know the strain displacement. We want to find B. So B is a strain displacement relation. So this is our strain vector and this is displacement vector. So this is our B, strain displacement relation. Okay, so I can say this is B into displacement vector UE. So let's put the values here. Okay, B we know. Sorry, let's find B. B is equal to dou by dou x n transpose. N transpose is n1 and n2. By differentiation, we get the B matrix as minus 1 by L, 1 by L, which is of size 1 by 2. So let's try to understand how this size comes. Okay. We know this strain vector is 1 by 1. Okay. Displacement vector for this element type is 2 by 1. Okay, this one. And hence B should be 1 by 2. So if you notice, the one comes from strain. Okay, so strain number of strain components is 1. So B is 1. The first dimension is 1, whereas the second dimension this comes from displacement vector size. Okay, so this is 2. So this basically is degree of freedom per element. Okay. So the size of B matrix is 1 by 2, which is nothing but number of stress components by degree of freedom per element. Okay. So this one is number of stress component or strain components. We can also say it is a dimensionality of space or dimensionality of problem. So now let's see B matrix we have seen. We will see D matrix. So D is, as we know, it is a stress strain relation. So for 1D it is only one stress component. So this is 1 by 1, only one strain component, and therefore D is 1 by 1. Okay. So we can set sigma x as sigma stress vector. E is our D matrix. Okay, and this epsilon x is our strain vector. So now the size of D, if we see, it is simply a number of stress components. Okay, so for 1D case, it is, or we can also dimensionality of problem or number of stress components. So for 1D case, we have only one stress, so 1 by 1. 2D, we have three stress components. Okay, uh, remember that stress and strain are tensor, but we represent them as a vector. So in 2D, we have three stress and three strain components. So size of D matrix for 2D case is 3 by 3. We can also write like this. Sigma is 3 by 1 vector. Epsilon is 3 by 1 vector. So D is 3 by 3 matrix. Similarly, for 3D, we have 6 stress and strain components. So size of D matrix is 6 by 6. And we can say stress vector is 6 by 1, strain vector is 6 by 1. Hence, D matrix is 6 by 6. So to just summarize, okay, the B matrix is the first dimension is no, number of stress components, whereas second one is degree of freedom per element. And D matrix size is simply a number of stress components. So no, before finding the K matrix, element stiffness matrix for 1D bar element, let's see size of B matrix for different element types. So strain vector is related to displacement vector by B matrix. And let's see it for 2D and 3D elements, some popular element types. Okay, let's talk about 2D first. So for 2D is epsilon E is 3 by 1. Number of strain components are 3. Okay, that is epsilon 1 1, epsilon 2 2, and epsilon 1 2. Two normal strain components and one shear strain component. And B matrix, as we know, the first dimension is number of strain components, so 3 by the second one is degree of freedom per element. Okay, so it depends on element type. So then UE, which is again degree of freedom per element by 1. This is DOF per element. So let's say for first order tri-element, which has 3 nodes. Okay, and since it is a 2D element, each node has 2 degrees of freedom, that is displacement or translation in x and translation in y. So we have 3 nodes, so 3 into 2 is a total degree of freedom per element. So U vector is 6 by 1. B matrix, as mentioned, it is number of stress components or strain components by degree of freedom per element. So 3 by 6. For first order quadrilateral element, it has 4 nodes, so degree of freedom per element is 8. So UE is 8 by 1. B matrix is number of strain components by degree of freedom per element. Second order tri-element has 6 nodes, so 12 is total degree of freedom per element by 1. B matrix is number of stress components by degree of freedom per element. Similarly, second order quad element has 8 nodes, so this is 20. This is 16 by 1. B matrix size is 3 by 16. Now let's see some 3D elements. So for 3D, in 3D we have 6 strain components. So strain vector size is 6 by 1. B matrix, the first dimension is number of strains by DUF per element. And displacement vector size is DUF per element by 1. So let's say for first order TET element, it has 4 nodes and each node has 3 degrees of freedom. Okay, that is translation in X, translation in Y, translation in Z. So 4 into 3 is a 12 degree of freedom per element. B matrix is number of stress components 6 by DUF per element. So 6 by 12. Similarly, first order has 8 nodes. So 8 into 3, 24 degree of freedom per element. B matrix size is 6 by 24. Second order that element has 10 nodes. So 30 degree of freedom per element. B matrix is 6 stress components by degree of freedom per element. Second order hex element has 20 nodes. So 60 by 1. This is 6 by 60. So the purpose of this exercise is to understand the size of B matrix, okay, and how it depends on dimensionality of problem or space and element type. So hope this B and D matrices are clear. Now let's come back to 1D bar element. We have B matrix and D matrix. Okay, B matrix is minus 1 by L, 1 by L, and D matrix is simply E. Okay. So we will substitute B and D here and derive the element stiffness matrix for 1D bar. So B matrix, this is B matrix, then B transpose and D matrix E. So this is 2 by 1, E is 1 by 1, and this is 1 by 2. So this matrix multiplication rule, we get 2 by 2, the size of K matrix. So E, I will take it out. Let's take it as a linear elastic material. So E is constant, okay, and A is also constant. So multiplying this matrix with this, we get 4 terms in 2 by 2 matrix. So this is 1 by L square minus 1 by L square minus 1 by L square and 1 by L square. So let's simplify this. So we get A by L square, we will take it out, and inside we have 1 minus 1 minus 1 1. So this integration of this 2 by 2 matrix is integration of each term. So this integration will go inside the matrix. Okay, so we get the terms like this. So integration from x equal to 0 to L, 1 dx is L. So here we get L, this is minus L, this is minus L, and this is L. So further simplifying, we get element stiffness matrix as A by L 1 minus 1 minus 1 1 for 1D bar element. in 1D space. Okay, this way, we can put all the B and D matrices for different element types in a generic form of K, and we can derive element stiffness matrix for different element types. So B and D will change for different element types and depending on dimensionality of problem. In next lecture, we will see for linear first order linear or linear tri-element and first order quadrilateral element. Okay, so let's highlight some important points here. Okay, so we can observe that while deriving K matrix, we are doing integration inside the matrix. Okay, so integral needs to be performed for each element in assembly. Okay, we may have 1,000 elements. We need to do integration for each element. Okay, and other thing is integral is performed for each term in stiffness matrix. So if this is only one, this is only stiffness matrix for one element, but the integration or integral is done 4 times because we have 4 terms in this matrix. So integral is performed for each term in element stiffness matrix. And in FEA steps, we know the FEA steps are first we write element stiffness matrix for each element. The second step is we perform assembly of elements, right? So for example, if we have, let's take this assembly or some structure. Okay, let's now divide, instead of one element, we will split the structure into 1, 2, 3, 4, 5, 6 number of elements. Okay, so this is x equal to 0, this is x equal to 1. Let's take length of each element is same, 1 mm. So x equal to 3, 4, 5 and x equal to 6. Okay, so for this element, the stiffness matrix integration is performed over x equal to 0 to 1, okay, and remaining terms. Okay. Then for this element, okay, let's say this is element 1, this is 2. Okay, so element 2, to find the element stiffness matrix for this element 2, we need to perform integration from x equal to 1 to 2, okay, dx. Similarly, for this, the limit is x equal to 2 to 3, then x equal to 3 to 4. Okay, and for last element, it is the limit is integration limit is x equal to 5 to 6. So what I'm highlighting here is that for each element, the integration limit is different. Okay, so that's what integral needs to be performed for each element separately because the limits are different, because elements no their coordinates are different. Okay, and apart from that, no, always the L is not going to be same. Okay, the length of element may not be same. For this element, it may be L1, L2, and so on. Okay, L5. Okay. So what the important point here is how complex, given large assembly of elements, how complex the calculation of stiffness matrix for each element. Okay, because limits are changing, the terms are also changing, coordinates are changing. So that is the main and important point.